In a parallel circuit having 3 bulbs, each bulb has its own path from one terminal of the battery to the other. There are separate pathways for current, one through each bulb. In contrast to a series circuit, the parallel circuit is completed whether all, 2, or only one bulb is lit. A break in any one path doesn't interrupt the flow of charge in the other paths. In a series circuit, each bulb had the same current. In a parallel circuit, each bulb has the same voltage. In this parallel circuit, a 9-volt battery provides 9 volts across each activated bulb. Here's some characteristics of parallel connections. Each device connects the same 2 points A and B of the circuit. The voltage is the same across each device. The total current divides among the parallel branches. The amount of current in each branch is inversely proportional to the resistance of the branch. The total current is the sum of the currents in all the branches. As the number of parallel branches is increased, the total current through the battery increases. From the battery's perspective, the overall resistance of the circuit is decreased. This means the overall resistance of the circuit is less than the resistance of any one of the branches. Electric circuits are frequently described by simple diagrams called schematic diagrams. Resistance is shown by a zigzag line, and ideal resistance-free wires are shown with solid straight lines. A battery is shown by a set of short and long parallel lines, the positive terminal with a long line and the negative terminal with a short line. These schematic diagrams represent a circuit with 3 lamps in series and a circuit with 3 lamps in parallel. Sometimes it's useful to know the equivalent resistance of a circuit that has several resistors in its network. The equivalent resistance is the value of the single resistor that would provide the same load to the battery or power source. The equivalent resistance of resistors connected in series is the sum of their values. For example, the equivalent resistance for a pair of 1 ohm resistors in series is simply 2 ohms. The equivalent resistance for a pair of equal resistors in parallel is half the value of either resistor. The equivalent resistance for a pair of 1 ohm resistors in parallel is 0.5 ohms. The equivalent resistance of 2 8 ohm resistors in series is 16 ohms. The equivalent resistance of 2 8 ohm resistors in parallel is 4 ohms. For the combination of 3 8 ohm resistors, the 2 resistors in parallel are equivalent to a single 4 ohm resistor. They are in series with an 8 ohm resistor, adding to produce an equivalent resistance of 12 ohms. If a 12-volt battery were connected to these resistors, the current through the battery would be 1 ampere. On the left you see a complicated arrangement of resistors. The equivalent resistance can be reduced down to 10 ohms. Electric current is fed into a home by 2 wires called lines. Each line has a voltage of about 110 to 120 volts. These lines are connected to wall outlets in each room. The voltage is applied to appliances and other devices that are connected in parallel by plugs to these lines. As more devices are connected to the lines, more pathways are provided for current. The additional pathways lower the combined resistance of the circuit. Therefore, a greater amount of current occurs in the lines. Lines that carry more than a safe amount of current are said to be overloaded and may heat sufficiently to melt the insulation and start a fire. Consider a line connected to a toaster that draws 8 amps, a heater that draws 10 amps, and a lamp that draws 2 amps. If the toaster is operating, the total line current is 8 amperes. When the heater is also operating, the total line current increases to 18 amperes. If you turn on the lamp, the line current increases to 20 amperes. To prevent overloading in circuits, fuses or circuit breakers are connected in series along the supply line. The entire line current must pass through the fuse. If the fuse is rated at 20 amperes, it will pass up to 20 amperes. A current above 20 amperes will melt the fuse ribbon, which blows out and breaks the circuit. Insulation that separates the wires in a circuit can wear away and allow the wires to touch. This effectively shortens the path of the circuit and is called a short circuit. A short circuit draws a dangerously large current because it bypasses normal circuit resistance. Circuits may also be protected by circuit breakers, which use magnets or bimetallic strips to open the switch. Circuit breakers are used in modern buildings because they don't have to be replaced each time the circuit is opened. That's the end of Chapter 35. Thanks for stopping by.